So welcome. So we're going to start the next chapter, which is the chapter on capacitance. Not a very long chapter, actually. We come back and use capacitances again later on when we deal with transient effects. That is time-varying effects. But this is laying down the foundation of what a capacitor is. So I'd like to describe capacitors to you. And the most common capacitor is what's called the parallel plate capacitor, which you can imagine is like just a plate of metal with another plate of metal that's close by, and in between them, connected to them, we have some kind of power supply. So a battery would be a very typical thing. And what happens is that the potential of this side tries to drive positive charges to sit on those plates, and the negative tries to drive a negative charge to sit on that plate. So it's still neutral. I mean, the whole thing is still neutral. Still the same number of electrons as protons, but they're separated. And that's what charge power supplies do. They separate charges. They make the positive go to one terminal and the negatives go to another terminal. Just in case I've not mentioned it, I think I mentioned it before, this is the electrical symbol for a voltage source, battery, power supply, that kind of thing. And it's basically a whole bunch of parallel plates, which is supposed to be like the two plates in a battery. That's where it comes from, really. And the long plate is the positive and the short plate is the negative. If I have a cell, it's only one of them. If I have a battery of cells, that's what a battery is. A battery of cells is a whole bunch of cells. Then I do it like that. If it is a power supply and I can change the voltage setting, the EMF setting, it has an arrow through it saying, hey, like a needle, you can change it. Okay. So just different ways of representing things. Sometimes for each different component, they'll put these little circles on the end as if it was, there's the terminals that you can plug into. And sometimes they don't. Okay. So I think of this as like a charge separator, and I'm driving, the positive charge is one way and the negative charge is the other. Now, can you tell me, which is it that actually moves? It's the electrons. And yet we think of the current as being a flow of positive charge, and that's fine. They had to think of it before they really knew what was going on, so they picked positives. And the reason why nobody changes it is because it doesn't really matter. Current is an abstract thing. It's the flow of positive charge. It's made up of electrons going in the other direction, but that's not the end of the world, you know. So sometimes we will picture things realistically and sometimes not so realistically. And so I want to do a bit more imagining here. So I put the first positive and the first negative. And now I'm going to try and put a second one up. So I try and put a second one up, and not so bad. These two positives are close together, and they don't want to be close together. So the first one was pushing back on the second one. So I had to do a bit of work to get that second positive charge on there. And this negative is next to this negative. It doesn't want to be, so I had to do a bit of work to force that on. But that's what my power supply can do. Electromotive force, EMF. So I can push things up there. You get up there. Add a third, add a fourth, add a fifth, add a sixth. I'm going to stop there. Problem. I've now got so many positives that adding the seventh requires more work than more energy than I can get out of this battery. I can't give the positive enough energy to fight against this repulsive force. And so that seventh charge is not going to make it. It's not going to go. I have a fully charged capacitor. So capacitors start off empty. You apply a voltage, you get them fully charged. I can do a number of things with them. I can take that capacitor that is fully charged. I can disconnect it from the battery. It's still fully charged. I can then reconnect it through a light bulb, what do you think will happen? Yeah, the negatives will flow this way and the positives will flow that way, and they'll light up the light bulb. Yeah, until the energy's used up. So I stored a little bit of energy and I used a little bit of energy. Charging, uncharging a capacitor. The energy is stored in the electric field, by the way, which is a bit abstract again. Yes?
So are those like weights and like the capacitor is like a, what is it holding? Where is it going? What's sitting there? Or I mean like, what are the charges going to? The capacitor?
So this is literally a metal plate.
Okay.
And they're just sitting on the metal plate. And then on this side, they're just sitting on the metal plate. So inside, there's air or a vacuum or... That's the field. So the electric field stores the energy. And I'm not going to get into quite how it does it. It's to associate with the field. Yeah. Okay. So I can use it as a storage of energy. Problem is, when you work out how much energy, as we'll work out later on, it's not much. We're much better off with the actual battery. Why don't I just take the battery and connect it to the... That's the smart money. Forget the capacitor, just use the battery. Well, there might be an environment where the battery is going to cause problems, you know, chemically. Might be an environment where I don't particularly want something like a battery hanging around. As long as I don't need a lot of energy, and as long as I don't want this charged up for months, sometimes I can use a capacitor as an energy storage device. Specialized equipment, I could do it. I can do it sometimes as a joke. Sometimes you'll have a situation where you have what looks like a book, and somebody hands it to you and you get a shock from it, and that's using a capacitor on it, you know. So if that's why we have them, then it's not a particularly good reason to have them, you know. It turns out the real reason why we have them, the majority reason why we have them, is because it takes time to charge up and discharge the capacitor. So if I have a power supply and I turn the power supply on and I turn the power supply off and I turn the power supply on and I turn the power supply off. So this is my voltage versus my time. If I look at, for time, if I look at the charge on the capacitor, what happens is, it starts charging up and it goes very easy, and then it gets harder and harder and harder, and then it stops. And then it starts discharging, and it discharges very easy. But then it stops. And it starts charging up, and it goes like that. And there's a sluggishness. Rather than this sudden increase, there's a sluggishness to the way the capacitor behaves. And the bigger the capacitor, the more sluggish it is, if you like. Now, what we find is, so this was for charge, let's just be, because I want to draw another diagram, which is the current, the flow of charge. And what we find is the current is very quick to begin with and then falls off. I don't know if I drew that right. Yeah, and it's very quick to begin with and then falls off. I'm not sure I'm drawing that right, but various graphs for different aspects of the capacitor's behavior when you are interested in time. These are called transient effects. In particular, what you find is that capacitors are transparent. I'm using fanciful language here. Transparent at high frequencies. But capacitors are opaque. I spell opaque, O-P-A-Q-U-E, at low frequencies. And I'm going to put that in inverted commas because what I mean is you don't notice them at high frequencies, but you sure notice them at low frequencies. And so they are very useful for getting rid of what's called DC, or constant voltage effects. They're very useful for being a high-pass frequency filter. And it turns out that they are complementary to a thing called an inductor, which is a low-pass filter. And so the two of them tend to work well in tuning circuits. So we're going off in, that's where we're going to use them a lot. We've got to learn a bit about them to begin with. So capacitors are very useful. They're used in electronics for signal processing more than they are used for energy storage. That's the kind of take home. So let's define a capacitor. A capacitor's capacitance is the magnitude of the charge stored on one plate of the capacitor per volt potential difference applied across the capacitor. Oh my word. So if I have my capacitor and I have a whole bunch of positives here and a whole bunch of negatives there, it is the capacitance equals the charge per volt. This is delta V. It's the charge per volt. It has base units would be coulombs over volts, which we call the farad, which is the F. 1 farad equals 1 coulomb over 1 volt. Capacitance is a scalar quantity. It doesn't point in any direction. It's just, it is. If I could somehow get more charges on here for the same voltage, I would have more capacity, more capacitance. By the way, and I was careful up here to point it out, it's not the number of coulombs on both of them. It is the number of coulombs on either one of them. So, frankly, if you add up the coulombs are positive to the coulombs are negative, you get 0 anyway, you know. But sometimes people will say, well, I got 5 coulombs of positive, so that means I have 5 coulombs of negative, that's 10 coulombs. That's not the way it works. It's just the charge on one of the plates. Yeah. Cool. How much charge can a 9pF capacitor, what's PF stand for? Pico. How much charge? Have you not got this?
No.
Have you got that?
Yes.
Oh, I added this in. Sorry. So how much charge can a 7 picofarad capacitor hold when a 4 millivolt potential difference is applied across the terminals? I like to do my voltages vertical. I like to do my batteries vertical. And I like to do my components like this. You don't have to do them like that. But I like the idea that that positive potential is a higher potential than that negative potential. I'm trying to always draw the analogy to a pump sending water through pipes, and one side being a high, pressure, and the other side being a low pressure. I'm trying to draw that analogy. And I know my capacitance equals 7 times 10 to the, what's a pico? Minus 12 farads. And I know my voltage. My voltage is equal to, for, what's a milli? Volts. Language. If it's here, it's an EMF. The power supply creates an electromotive force measured in volts. there's no potential drop in the wire. So if this is 2 volts positive, this is 2 volts positive eventually, when we're in steady state. If this is 0 volts, this is 0 volts, because the wire in the steady state does not support a potential difference. It's a conductor. Yeah. Now, we're interested often in before steady state, but in the steady state, they're the same. So if I have 6 volts here, I have 6 volts across this. If I have 9 volts across my battery, I have 9 volts across this, because there's only one component. Yeah. In the device, I call it a potential difference. So voltage on your power supply is called an EMF. Voltage on your component is called potential difference. It's like salary versus spending money. It's the same stuff. It's just we call it salary when it comes out of the bank, when it comes out of the company. We call it spending money when I take it out of my bank account. It's the same stuff. The energy per coulomb from the battery, I'm going to call it EMF. The energy per coulomb in my device, I call potential difference. Just terminology. So I say, what is how much charge? So capacitance equals charge divided by voltage. So charge is equal to capacitance times voltage, which equals, better stay in SI units. So 7 times 10 to the minus 12 times 4 times 10 to the minus 3. My charge is going to be equal to, it's going to be 28 times 10 to the minus 15. What's that going to be? Coulombs. Am I right on that? Did I do that right? Notice, please. What's this C stand for? What's this C stand for? Who made this up? So
is one supposed to be a lowercase c then?
No. So, by all means, as long as I can read it, put curly things on, but know it by context.
And then the diagram, it says charge C, isn't it charge Q?
So, where's the diagram?
That little graph.
What I did? Where? No, charge in coulombs.
Okay.
Yeah. See, it's like, we ran out of letters. We used all the Arabic ones. We used the Greek ones. Yep.
For capacitance, can we put down CAP instead of just C?
You can, but it's going to make your equations a bit longer. But yeah, as long as you know what you're doing, as long as when you communicate it's clear to me, you can't put down CAP like that because I'll think that's your capacity. I think that's well, what would I think about that? I'd be very confused because that could be amps, So to help me out here, but all I'm saying is, sometimes just make it so that you don't make a mistake over what it is. It's easy to do. And so for a bright, casual student, somebody who's bright but not paying that much attention, that's the mistake they'll make. They'll go, oh yeah, this is C, that means charge. And well, no, in this case it means capacitance. So don't just learn the equations and turn up on the day, because you won't know what the letters stand for, Okay. Which trace best represents the relationship between the charge on a capacitor and the potential difference across the capacitor? So we need to talk about charge on the capacitor, which is Q, and the potential difference, which is V. So I need a relationship that links them, and wouldn't you know, it's capacitance equals Q over V. Now I want Q to be on the y-axis, and I want V to be on the x-axis. So rearrange this. So I want Q by itself. Q is equal to C times V. Okay. Now that's my Y. Sorry, that's my Y. And that is my X. So that's my slope. This is linear, isn't it? So this is linear, that's D. It's not B, it's D. So some people can look at this and they've got to be careful. You've got to kind of like, and I use a different coloured pen sometimes, or if I've only got one pen, I'll really score it in so that I recognize that this is charge and this is potential, and I am being sure to represent to me what my parameters are, what my axes are. So there's my y-axis, there's my x-axis, oh, this is linear. It doesn't matter so much for this, but sometimes if I say that energy is equal to 1/2 mv squared, and I say to people, plot N, energy versus V, they'll look here and they'll go, well, that's energy and that's my V, so it's just going to be linear. But I'm not plotting it against V squared, I'm plotting it against V. So you've got to remind yourself, oh, I'm only using V, not the squared. So it's really worthwhile on this to mark somehow what your two axes are, what the letters are, and then look at the expression. Some people can see that's linear. For other people, they have to do a table, Q, V. And what I recommend you do is you go, well, V's on the bottom, so go 0, 1, 2, 3, 4. And then you say, okay, so if V is 0, Q is 0. If V is 1, let's say that C is 1. So let that equal 1, just to make it simple. So that's going to be 1. If V is 2, 2 times 1 is 2. If Z is 3, 3 times 1 is 3. If V is 4, 4 times 1 is 4. Oh, yeah, that's going to go like that, like that, like that, like that. Linear. Not like that, like that, like that, like that. So that B is to catch people who just say it's linear, but they don't reckon which way around it is. Yeah? I'd like you to get to the stage, we've practiced doing these traces before. I'd like you to get to the stage where you can actually do a simple graph by yourself like that, without me giving you any numbers to begin with. It's very disconcerting when you first do it. So let's talk about a parallel plate capacitor. Oh, that's a bit missing, I'm sorry. So in principle, think of it as being two parallel plates, a plate with a gap. The most common type of parallel capacitor, is the parallel plate capacitor. It consists of two parallel conductors that are isolated from each other. One plate can be charged positive while the other is charged negative. The capacitance of the parallel plate capacitor depends upon the cross-sectional area and the perpendicular gap size. And that kind of makes sense. Just to ask yourself, if I increase the area, I have more charges. So that's got to mean more capacitance, surely, yeah? If I go 4 times the area, I can have 4 times the charges on there, surely, yeah? So that the area should go on top. And then you say, well, what about the separation? And you say to yourself, will separation have any effects? And the answer is pretty much yes, you're dealing with an electric field. Then you can say, well, if the does the capacitance get bigger as the area, as the separation gets bigger? If that were the case, then my biggest capacitor would be the one with the biggest gap. So a plate on Australia and a plate on America would have a huge capacitance. Well, it's clearly not the case. So it can't be on the top. It must go the other way. So it's got to be underneath. That small gaps give you a big capacitor. And then you say to yourself, well, is it D or is it D cubed, D squared? And unless you're seeing a radial symmetry, a spherical symmetry, I would not put D squared down. D squared, 1 over D squared comes from a spherical, inverse square relationship, comes from a spherical symmetry. So 1 over D, and then I need a constant proportionality, and I get my epsilon naught. Epsilon naught is permittivity of free space. Permittivity of free space. And it's a fundamental constant of the universe. And in lab today, you've either found it or you will find it, depending on which lab you're in. So there's my expression. It kind of makes sense. Supposing I decide to fill the gap with stuff. Well, hopefully insulating stuff, because if I fill it with conducting stuff, then the charges will just flow through it. So the only really interesting choice is to have a stuff that's insulating, and we call this the dielectric, insulating. And we can think of examples such as a vacuum can be regarded as being insulating. Air is pretty insulating. Paper is a good example. Then mylar, M-Y-L-A-R, I think, and other polymers. Sometimes you'll get paper impregnated with oil. My first research project was Plessey, electronics company in Britain, were trying to make better and better capacitors. And they found that by putting exotic dielectrics in, they could improve the capacitance of the capacitor quite remarkably. So they had these impregnated papers that were some very exotic stuff going on. And the only problem was that the chemicals they used were fetal phobic. So if anybody on the production line fell pregnant, it was a disaster. And to some extent, if anybody at home had a capacitor that broke, it could be a real disaster. But mainly because of the concentrations of people on the production line. And so they wanted to try to get the same electronic effects without having the same chemistry. So part of my job was to try to implant what they thought were the essential features of this chemistry using ion implantation. So that was where it came from. And making a more capacitive capacitor is worth a lot of money. It's a lot of things. Why should putting and so the figure of merit, the thing the thing that represents how significant the dielectric is in increasing the capacitance is this thing called the dielectric constant. This is the dielectric constant. It's given a value k, and the value k goes from 1 upwards. You can't have less than, well, I suppose, that's an interesting point actually. If I had something that had somewhat conducting properties, would it be less than 1? Kind of like a bona fide dielectric, typically you'd regard vacuum or air as 1, and you'd want a number bigger than that to make it useful. So you'd look for something with a dielectric constant of 5 or 7 or something like that. So it's a multiplication factor. Why should putting a insulator between two parallel plates improve my capacitance? And for that, let's just look at this picture. So I've done a cell. I have my 2 plates. And okay, I put my first pair of charges on, and then I put my second pair of charges on. And then I put my third pair of charges on, I put my fourth pair of charges on, put my fifth pair of charges on, and now it turns out my battery is not strong enough to be able to put any more charges on, so I am fully charged. So my capacitance is set. I have a certain voltage, I have a certain charge, my capacitance is equal to that Q over that V, and I am done. That's my capacitance. But man, if I could just add some more charges without adding more voltage to cause it, then it would really be helpful. And so what I do is, somebody came up with this idea about, let's put this material in between, and empirically it works really nicely. But what is in fact going on? And what's going on is, basically, if I imagine an atom, I have the positives in the middle, and the negatives are a cloud around the outside. So it's spherically symmetrical, and it's basically neutral. But if I put this inside an electric field, then I'll pull the positive charges slightly to one side, and I'll pull the negative charges slightly to the other side. And I can represent that as a negative positive combination. I'm just slightly polarizing, it's called. I slightly polarize the atom. So I'm just going to show one atom, but if I can polarize the atom in between, well, that becomes slightly positive, that becomes slightly negative. Did I say that the right way around? I'm not sure I did. Now, when this next positive charge wants to work its way along here, it does not see these 5 positives keeping it away. It sees these 5 positives reduced by the proximity of these negatives. So it sees like 2 charges. So I can easily get on there. Now I've got about 3 charges. Now I've got about 4 charges. Now I've got 5 charges. Can't do any more. So the proximity of these polarized charges to these charges from the circuit means I can add more charge, add more charge, add more capacitance. So it's a real win-win situation. Put a piece of paper in between, you'll get more capacitance. And actually what makes it even more interesting is, have you ever tried keeping 2 pieces of metal separated from each other over big areas? I mean, they're gonna touch each other somewhere. But what you can do is you can take a piece of metal, foil, let's make it foil so it's cheap and it's light. I put paper over it. I put a piece of metal there. So the top piece of metal sticks out that side and the bottom piece of metal sticks out that side and the insulator's in between. And you roll it, then it automatically separates itself. The paper is the gap, and the gap is the paper. It's perfect. You get a machine that just rolls capacitors. Very inexpensive, very nice quality. Want a bigger gap? Use thicker paper. Want a thinner gap? Use smaller paper. It's great. Okay. How big is the gap between the plates of a circular air-filled 3 microfarad parallel plate capacitor that has a radius of 4 centimeters? Can you do that one for me, please? I guess I've got to tell you what epsilon naught is. Epsilon naught is equal to, I think it's 8.8, I think it is, times 10 to the minus 12, something or others. I'm going to look it up. I don't carry that in my head. So let's have a quick look. Oh, close. Let's have a quick look. So this is going to be, I'm going to pause this for a second so you don't hear me doing it. So we're back. Let's just see how people are doing. Stop. And then let's look at the graph. Mainly a bit of B, some C, bit of D. Let's have a look and see what it is. So my visualization, I kind of cheated and used the diagram over here. It kind of represents, you might not be given a diagram, but it's basically, there's my radius, here's my separation. So the area is the area of the cross-sectional area of the gap in between. And we know that C is equal to, and I like to work in SI units, so it's got to be 3 times 10 to the minus 6 farads. And my radius, well, that's going to be 4 times 10 to the minus 2 meters. And my epsilon naught, and I gave you this value, 8.8 times 10 to the minus 12. And it is seconds to the 4th area, not area, amps squared, meters cubed, kilograms. It's weird units, but that's the way it is. And the basic equation we're going to use is we're going to turn around and say, well, my capacitance is equal to K. That's my dielectric constant, A epsilon naught over D. I want to find out D. So D is equal to K, A epsilon naught over the capacitance, which equals the K value, I would tell you this, I would hope you know it, but the K value for air and the K value for vacuum is 1. If you were stuck in a test and you said, I can't remember what it is, I'd probably give you it because it's question or comment. I'm sorry? No units for K. It's a multiplication factor. It's just a figure of merit, basically. So we have that. Then the A, well, of course, you have to know that that equals K pi r squared, not 2 pi r. It's got to be pi r squared. That's why we learned those equations. Over D. So this will be that times pi times 0. What was it? No, I'm using the other way. 4 times 10 to the minus 2 squared times 8.8 times 10 to the minus 12 all over. And it's going to be over C, which is 3 times 10 to the minus 6. And I worked this out on my calculator. Pi times 4 second EE to the minus 2 times 4 times 4 EE second EE to the minus 2 times 8.8 times 10 to the minus 12 over 3 times 10 to the minus 6. And I get 1.5 times 10 to the minus 8 meters. Cool. So it's A. And if you didn't get it, just have a look and see why. What was it that you didn't get? Did you forget to square it, or did you use 2 pi r squared, 2 pi r, or 2 pi r squared? Sometimes people use. Don't give points away for that. Give it away for the hard stuff, not for stuff like that. So. Cool. So next little thing, bit of a change of pace. So the world being the way the world is, they're not going to make a million types of capacitors. So you buy a standard size capacitor, and then you've got to try and get the capacitance that you want. And so you're going to be combining capacitors, and you're trying to make the capacitor either bigger or smaller. And if you think about it, if physically we know the capacitance is equal to K A epsilon naught over D, then if I can increase the area of the capacitor, I have a bigger capacitance. Now, this piece of conducting wire touches the top plates altogether. Isn't that like just making a capacitor with a bigger area? Isn't that what I'm doing here? I'm just making a capacitor. Just move them side by side and let them touch. So this one, so this is called parallel. Why is it called parallel? And the way you tell parallel is you look and see, is there a junction that I can take several routes through? They are in parallel. So if it's in parallel, I'm basically making the capacitance bigger. And so the capacitance of a parallel network is equal to C1 plus C2 plus C4 plus C5 plus C6, as many as you got. Just add them up. And it's because you're adding up the areas. And the sum, I've justified here in terms of, you know, capacitance and the charge and all that, but just increasing the area. If I make my gap bigger and I'm making my capacitance smaller, well, that happens when it's in series. Series means a point of interest. A point of interest has to go through the first one, then the second one, then the third one. There's no way around the sides. That's series. And so I want to make my capacitance smaller. And the way I make it smaller is 1 over the series equals 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C4. Most common mistake, people get these backwards. So they think the equation for series is the equation for parallel. So my advice is you write down C par and C ser, so you know. And then the second mistake is people don't, so always try and write in full sentences. Don't put down C1 plus C2 plus C3, because that doesn't equal anything. That's like a phrase. That's like saying frogs have shoes. It's meaningless. But if you say rich frogs have shoes, it's a sentence. So you write down C parallel equals. Because then you're going to write down not C series equals, which is what people do. They write down that bit, 1 over C1 plus 1 over C2 plus 1 over C3. And then they get an answer and they go, oh, that answer must equal my answer. Well, no, because I'm asking you for C series. 1 over C series is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And people forget to flip their answer because they're not thinking in sentences. So again, why do I do this? Because when I came back into teaching, I would make slips all the time. And I made them whenever I was nervous. So I made them whenever I was doing stuff in front of the class. And my students make slips all the time. They make them when they're nervous, which is in a test. So we've both got to find ways of minimizing pointless slips. And so one of the ways is you write incomplete sentences, because it's a shame to do all the mathematical stuff and then really through lack of thought just assume, oh, that must be C series, when clearly it's not. Because, you're supposed to have a smaller answer, and anyway, it doesn't work. So, watch out for that. Know those two equations, please. What is the equivalent capacitance of a network that consists of a 3 nanofarad capacitor, a 4 nanofarad capacitor, and a 12 nanofarad capacitor connected in parallel? So, first capacitor, second capacitor, third capacitor, and this is 3NF, this is 4NF, and this is 12NF. And I go, they're in parallel. C par is equal to C1 plus C2 plus C3. I'm going to write that down 1,000,000 times because I don't want to forget it as I get old. So C par is equal to, I'm torn now. Shall I just leave it in nanos, or shall I convert into base units? They're all in nanos, so you can cheat a little bit, and you can go 3 plus 4 plus 12 nanofarads, which equals 12, 16, 19 nanofarads. You just add them together, piece of cake. On this one, what is the equivalent capacitance of a network that consists of a 3 nanofarad capacitor and a 4 nanofarad capacitor and a 12 nanofarad capacitor? 3 nanofarads, 4 nanofarads, 12 nanofarads connected in series. 1 over C series is equal to 1 over C1 plus 1 over C2 plus 1 over C3. That's my warning bell. So I say that equals 1 over 3 plus 1 over 4 plus 1 over 5. So this is going to equal, let's have a look. Oh, is it 5 or 12? 12. So find the common denominator. That's going to be 4 over 12 plus 3 over 12 plus 1 over 12, which equals 8 over 12, 1 over C series. So C series is equal to 12 over 8, which equals 12 over 8 is equal to 1.5 times 10 to the, 1.5 nanofarads. Notice, in a series, in a parallel combination, the answer is bigger than even the biggest. In a series combination of capacitors, the series combination is less than even the smallest. Yes. You got to flip your answer. If you put down C series equals 0.66, no good. And I'm going to be mean about it as well, because it's like, it's giving points away. Hold on. We ain't finished yet. We've got another couple of seconds. So what do you do about this?
Add up the parallel first and then add a series?
Why the parallel first? You're right, but why the parallel first? Why not the series first?
Because that's the first circuit in the series.
Well, no, I don't think that's a good justification, because I can...
Gotta get the third value, and then you throw it in.
So it's what's unambiguous. And these two can be combined to form, which is then in series with these guys. But these, so this is in series with those, and this is in series with those. So which is we're going to be resulted if you do the series first? These are parallel to each other, unambiguously. Yeah? So I go, I don't know I've got time for this, but I'll give it the old try. So 2 and 4 and 3 and 12. So I go like this. I go, okay, let's combine these two together. They're in parallel. That makes it bigger. Oh yeah, C parallel is equal to C1 plus C2. So C parallel is equal to 2 plus 4, which equals 6 farads. Six plus 3 plus 12. C series, 1 over C series is equal to 1 over C1 plus 1 over C2 plus 1 over C3. 1 over C series is equal to 1 over 6 plus 1 over 3 plus 1 over 12, which equals 2 over 12 plus 4 over 12 plus 1 over 12. 1 over C series is equal to 4, 5, 6, 7, 7 over 12. So C series is equal to 12 over 7, which equals 1.7. 1.7 farads. So, two simple bits, but they get added together. And realistic circuits get more and more complicated, but you get used to picking them apart. It's like eating spaghetti. It's knowing where to begin on them. Next time, we'll do this last little bit on energy of a capacitor. And I will see you. If I don't see you again, have a good... Oh, remember, no, there is school on Monday on this campus. We do come to work.